So we're very pleased this week to have Yuri Tschinkel from the Toronto Institute and the Simon Foundation, who will speak about Igusa integrals and volume asymptotics in analytic and adult geometry.
Good afternoon. Thank you very much for the invitation. I'm delighted to be here. It's my first talk here, actually, with your department. So the mathematics I want to address, the simplest case is counting lattice points in a circle. What is the observation? Is that the number of lattice points is estimated by the volume, and then there is some error term. And so what we want to do, we want to compute the volume, which in this case is easy, and then we want to show that the error term is actually smaller than the main term. That's why we call it the error term. And of course, you could ask interesting questions about the exact shape of the error term. Gauss's circle problem, deep conjectures about how small it is in the error term. But for us, the volume will be more important. Now let's look at this sort of a priori different problem. Let's look at rational points on the projective line. So rational points are just tuples of co-prime integers up to plus minus 1. And the height function, measuring the size of the rational point, is just taking a point and to square root sum of squares. So we could have taken a different height function, maximum coordinates or something like this, maximum absolute values, but let's stick with this one. So it's essentially the same counting problem. So we want to look at rational points of height less equal than b. And so these are some lattice points in a circle. And there is, of course, a coprimality condition that we have there. But if you forget the coprimality condition for a moment, then we find, as expected, that the number of lattice points should be pi r squared. And then there is some correction factor, which is 1 over zeta 2 times 1/2. So the 1/2 is easy to understand with the plus minus 1 that's out there. And so how do we think about 1 over zeta 2? Well, we want co-prime. And what does it mean to not be co-prime at some prime? It's 1 over p. And then everything is squared. P to divide both. 1 minus 1 over p squared is probability of the prime. You take a product, you get product of terms like 1 minus 1 over p squared. And then you get 1 over zeta 2. Yes, so maybe for one such as case, we are counting lattice points in a circle. And so we find that the number of points is the volume times some correction factor. Now let's look at the leading constant one more time. So what is this 1 over zeta 2? I just explained that it's 1 minus 1 over p squared, product over all primes. But let's factor it as written. And let's interpret this as the number of points on P1 over a finite field Fp, which is p plus 1, divided by p times 1 minus 1 over p. And so that will be important for the future discussion. And we will interpret this answer later, more general setup, as some kind of volume, not at the real place, but rather at the adelic space. And here we're talking about the finite adels, because at the real place we saw is pi r squared, and so that's a contribution from the finite adels. But all with respect to what?
How you got zeta 2 again? I'm sorry.
Yes, so you want lattice points in a circle, right? But you have a condition that the GCD of 0 x1 is 1. So what's the probability of, no, that's P1 over, so number P1 of Q. So we want to think of this as x x1 and p squared minus 0, primitive, right? Plus minus 1. So you want to assume that they're coprime. And not to be coprime means the prime is to the right this n z, so that's 1 over p squared. And then the complementary thing is 1 minus 1 over p squared, and then you take the product of all primes. So that's heuristic. But of course, then you prove that the heuristic is exactly what happens. And so now we're seeing this 1 over integral 2, and I'm explaining that that's actually a number of points in P1 of a finite field, regularized by this factor 1 minus 1 over P. So now let's look at this different problem. We understand P1 and then maybe Pn, it's the same story. But now let's look at some hypersurfaces in projective space. And the problem is the same. You want to count x0, x1, x2, x3. Again, 4 tuples, primitive, plus minus 1, of height less equal than b, here less equal than 1000. And we want them to satisfy this equation. So geometrically, it's a singular cubic surface. It's a unique E6 singular cubic. And we're looking at rational points. And this visualization, here we assume we're looking at some quadrant, x0 and x2 are bigger than 0. Otherwise, the points would be all over the place and we won't see them as nicely. But this is what we see. They're all over the place. And here you some lines.
Wait, what does the solid part mean? Is that means there's so many points that it looks solid? Or?
No, it's just the real points. I mean, it's very, yeah. It's hard to represent the surface, the points of it, so that maybe the colors will put it better, but this is what it is. And, okay, that's just a plot. You generate them. You run over all x0, x1, x2, x3, and then you look and you plot them. But there is a theorem which says that if you look at rational points of the complement of the unique line, given by this equation, then in fact you find b log b to the 6 times a constant c as b goes to infinity. And so here is the complete answer. The constant is the product of 3 numbers. The one is alpha is 1 over 6 something. The other one is 1. So you'd say, why you're writing this 1? You could have omitted the 1. But it should be there. And the other one is a product, again, over local factors, where this time the local factors look like this. B squared plus 7p plus 1 over b squared, and then 1 minus 1 over p to the 7. And so what is this? Well, this is the number of p points on, well, actually the singularization of the cubic. So why do we have this 1 minus 1 over p to the 7? So let's look at the number of p points on a cubic surface. You may have heard that the cubic surface, split cubic surface, is obtained by blowing up p2 in 6 points. So how do you count number of p points on a cubic surface? You take p2, which is p squared plus p plus 1, and then you get rid of the points that you blow up, the 6 points, and then you put back in the lines, right? That will be the blown up points. And this way you come up with p squared plus 7p plus 1 over p squared. Now, if you try to take a product over all primes, then you realize that it's not convergent, there is a problem here. The main issue with all the products is, of course, the term 1 over p. The constant at this a over p, that thing has to be regularized away.
I'm sorry, I didn't understand the logic at all. In going through the picture of the cubic as a blow up to do this count, what is the logic?
So I just explained how to count the number of p points on a cubic surface, which is over a finite field. So thinking about the cubic surface as a blow up of p2 and 6 points. So blow up of p2, I'm just replacing the point by a line.
Yeah.
That's what you do. So you look at...
So minus what it is for P2, minus 6
plus p plus 1 times 6. That's how you get, in the original P2 we had p squared plus p plus 1 points. So there was a p here. And as you introduce 6 more lines, it's 6 times p plus 1, so it becomes a 7. And then you can check that it comes out with a 1 idea. So this is really number of points on the cubic over a finite field over p squared. And 1 minus 1 over p to the 7 is there to regularize this otherwise divergent other product. And so that will be important. We will see with regularization factors.
What's the philosophy of allowing yourself to regularize?
So, so why do you want to regularize Euler products? In other words, yes?
No, that's not what I asked.
Why
Why are you allowed to choose a regularizing factor?
So, I'll show it, because otherwise the measure, you see, if you write down a measure, the divergent measure, an integral diverges, you don't want to do that. So you want to pull out the pole, so to speak, right away, and then you want to integrate the measure.
You just choose a way of
doing this, and of course the choices are arbitrary a priori, but then you show it doesn't matter how you regularize it. So we'll have
the
it more.
answer is you can show that what you ultimately want is well defined.
Yes, that's the key. So, all right, and so the infinite place contributes a density as well. It doesn't look like this, because the infinite place there are infinitely many points, but it's really a density. And so if you ask me what is this constant, then I can tell you. You take the cubic surface, now think about the reals, and it's a projective space, you have some kind of metric, and let's look at an epsilon neighborhood of the cubic surface. And then let's take the volume of that. And then let epsilon go to 0. And then let's look at the first term, that's going to be this integral. So it's some kind of volume, the residual volume of the cubic surface. And here it's an explicit form of that. So there are more examples, of course, and here we have a different cubic surface, and I've plotted points of...
Where was the 1,000 in the previous discussion?
This one?
Oh, there, it came from that.
What is this alpha?
Remember the 1,000? Height less than 1,000. Yeah.
This one? It's a height. So I just plotted more points here.
Oh, that was just your plot.
Just a plot.
Okay, fine.
And this is an asymptotic for arbitrary b as b goes to infinity. So the main term is that. And so this is the explanation. And so here I just plot points up to 50, and so this is what they are. For this very symmetric equation. And the bottom line is that you can, again, look at the asymptotic points of bounded height. And there are many, many cases that have been studied in the literature of singular Lopez surfaces, singular cubics, singular equiform Lopez surfaces by people in England and in France, and many results that prove asymptotic formulas in this context. And the framework, the conjectural framework that explains all such results goes back to Manin, who formulated the following conjecture. If you look at the smooth projected Fano variety over a number field, let's say over the rationals, and you can think for, it's your first encounter with Fano varieties, you can think of small degree, low degree hypersurfaces in Pn, like a cubic surface in P3. So if the degree of the surface is less than the number of variables, smooth, it's going to be a Fano variety. And already this case is quite interesting. And the anticanonical embedding is the preferred embedding into the projective space. Geometrically, the anticanonical passes.
Is that less than or equal to? It's
Sorry?
less or equal to n, right?
It's less than n plus 1. The degree should be less than the number of variables, less equal than n.
Right.
So then there should be some zariski open subset. On cubic surfaces, it would be the complement of lines. So that on that subset, the asymptotic is given by b log b to the b minus 1 times a constant, where b is the rank of the Picard group minus 1. I mean, the asymptotic is b minus 1. B is the rank of the Picard group. So again, the cubic surface, split cubic surface, rank Picard is 7, and log b to the 6 that we were seeing fits perfectly well with this conjecture. It's rank of the Picard minus 1.
Does conjecture so you kind of find x0?
So the conjecture doesn't tell you how to find x0. It says there should be some zariski open subset. And the necessity of such a subset is visible already in the example of a cubic surface. Because if you look at the line in this region, we've computed the asymptotic right there. It was b squared. And the conjecture predicts b times log b to the something, much less than on the line. So the line sort of dominates the asymptotic. So therefore, if you want a conjecture that takes into account the geometry of the global variety, you want to eliminate these accumulating subvarieties because they would distort your picture completely, right? If you take out the line and look at the complement and count points and the complement to that line, then what you find is something that has a global geometric description.
So B is the second Betty number for people that think of these things over the complex number.
So now, we do not know whether or not the points are Zariski dense to begin with. This is actually already a problem for a quintic in P5. Mine, of course, is much bolder. He says, well, the density he takes for granted, and the conjecture is much more precise than just density. It says not only are they dense, but moreover, that's their asymptotic distribution. But, some geometric techniques have been developed to prove density, cortex encodes. Some work I did with Joe Harris years ago. That was already very interesting, but for quintics in P5, it's unknown.
So your previous examples were actually always singular, right? You were looking at singular.
Here we're looking at smooth, yes.
So in terms of the relationship between the smooth situation and the singular situation?
You put your finger exactly, it's the problem. Most examples in analytic number theory right now are singular. It's very hard to prove asymptotic formulas for smooth Del-Petro surfaces, it turns out. So, especially smooth cubics are way out of reach. There are some results for some degree 4 Del-Petro surfaces, smooth Del-Petro surfaces, certainly not the general ones. But
why is that?
Why? It's very strange. I mean that maybe from some other point of view, the singular varieties are more complex, but from the arithmetic point of view, singular varieties turn out to be easier. I can't tell you why, but the analysis, I actually can't tell you why. So the way these things are counted, it's great. We can get into this discussion. How do you count points here? I said, well, let's lift them to a lattice, right? So that's essentially representing the point on P1 like integral points on this minus 0, right? And thinking about the GM action here, right? Which is, co-primality in the end. So you fix some integral representatives here, and here you have something to integrate. Well, you can do the same thing on the cubic surface or on the default Del-Petro surface. This is called the universal torsor for this veracity. And for projective space Pn, the universal torsor is affine space Pn plus 1 and so on. But for smooth cubic surfaces, the universal torsor is given by 81 equations and 27 variables. And what you would need to do is you would need to count lattice points, again subject to this height inequality, satisfying these 81 equations and 27 variables, which is complete madness. Now the universal torsor for the E6 cubics that was in the first example, that Brandon Hassett and I computed some 10 years ago explicitly. In this case, the universal torsor is a hypersurface, one equation. Now, one equation is easier than 81 equations. So when you degenerate a cubic, somehow the universal torsor degenerates and becomes much, much easier to handle. So that's the answer. But a priori,
physicists use this idea a lot. They degenerate their computation and count. I've seen them use it.
And then, topology and algebraic geometry.
Here it's not so clear that the answer you get in the degenerate case has much to do.
That's right, because what we're looking at. So why do I love this? So we're looking at lattice, something very rigid. So rational points is like a lattice, it's like a rigid structure. But there is a lot of interaction with geometry. And this tension between geometry, like moving, and really geometric notions, global geometric invariance, is like lattice. That's the heart of the subject. That's the beauty of the subject. Now let's go to the next class of examples where we have a priori many rational points or integral points where we don't need to worry about the Zariski density. Proving that there are points on some hypersurface is hard, but let's use some dynamical system to produce many points. Let's look at some linear algebraic group. Reductive, non-reductive, doesn't matter. Let's look at some.
By the way, in terms of the symmetry, you keep mentioning it, it's just the Weil group of the corresponding. You've said like E6 cubic, so
Yes.
saying that.
So that's a singularity.
It's
It's a unique cubic surface with an E6 singularity. When you blow it up.
Oh, I see.
that's the-
Okay.
So, and there was another example. Yeah. So look at algebraic groups. Some rational have a number field and then some representation. And okay, so here's one example. You could have a representation so that the group has a risky dense orbit in it. So those are studied, they're called pre-homogeneous vector spaces, classified. This is theory. But we don't need to assume that. So we look at algebraic flows, right? We pick some point in the representation and just let the group translate your point. And then we could look at either rational or integral points, depending on whether or not you're looking at, well, okay, whatever you're looking at, in the orbit. Now, of course, it could also be, stabilizer and so on. So, and we can look at projective representations, then we would look at rational points, right? And the affine case will be integral points. And the problem that we then want to address is, let's count either integral or rational points in, let's say, G mod H. And again, I don't want to worry about the difference between G mod H of F and G of F mod H of F. Let's not deal with that. But, so that's our problem. So even for simple groups, let's say the additive group, GA squared or GA cubed, we can get interesting representations and interesting flows. And while we're still looking at the group, I mean, the group is not going to change, but the counting function is going to change. The counting function very much depends on which representation we choose. So there are many results for many asymptotic formulas in this equivariant setup. For example, for flag varieties, this was one of the earliest papers, and then for horospherical varieties, the equivariant compactifications of G mod U, or compactifications of the additive group, or so projective varieties, which have the group action, and the group has the dense open subset in there, and then the Cauchy varieties and so on. And then what we are seeing is that in all cases, the conjecture that I wrote down, and also its refinements, which address its leading constants, C, and so on, all the conjectures hold. And simultaneously, there was a lot of development in the study of integral points, using some ergodic theory ideas and mixing, and so I guess you could Nixarna, Gaskin McMullen, Rudnik, Radnikov, Brandl, Schwartz. Many papers in different situations, mostly for spherical varieties. So G mod H, when there is a Borel action on the other side of the dense orbit, and they prove asymptotic formulas as well. And of course, the original sort of example suggests that you would want to compare the asymptotic formulas with some kind of volumes, these volumes of height poles, right? But what you find is that not in all cases do you get this. There are some exceptions. So some of those exceptions can be explained by cohomological tools. So sometimes there is a constant factor difference. So sometimes you see you're expecting some number, you get 1/3 of that number. Why do you get 1/3? Oh, because some congruence class is actually not allowed. Or at 2 primes, there are some conditions for reciprocity that prohibit certain classes. And then you can explain those differences constant factors. It's much harder to explain differences in the exponents. And you do get other exponents. Nevertheless, we do have to address this problem. In this complete generality, can we compute the volumes of height poles? And so here is an example of what we want to compute. So consider 2x2 matrices. There's a fixed characteristic polynomial. All right, so what's the height function on it? Well, let's take sum of squares. So we have some matrix, ABCD. There's this condition. And that's the height. And what's the volume of the height pole? Well, there's some expression here, gamma factors. This is the residue at 1 of some kind of theta function for this quadratic extension here, with pi's and so on and so on. So some numbers.
Wait, are these supposed to be the analogs of the tau and et cetera from the previous line? I mean,
so this is the analog of the thing at infinity, for example, right? So, and here you can actually prove that the number of integral matrices in this ball of this height is this characteristic polynomial converges to this times the corresponding density. So there's a completely different, or there is a more general situation. Let's look at n by n matrices, fix a characteristic polynomial, and some condition that it has distinct roots. And then again, you can look at matrices of norm less than b, and to find b to the n is something, and some constant very explicitly. And as you can see, it's regulated class number, I don't know, some of this field extension that's coming from this polynomial, and then number of real places, pairs of complex places, with some gamma factors, and so on and so on and so on. It's quite complicated, right? So it's something that has been computed. Now, Mogoron generalized this further. So he looks at some semi-simple Lie group with trivial character, fixes a Haar measure. So now we're in the reals, yeah? Looks at some real representation and fixes some norm. And then he wants to look at the volume of a ball in that representation and for that norm. And what does he find? He finds an asymptotic formula, b to the a log b to the b minus 1, some constant, and a and b are defined in terms of combinatorial data, some relative root system, some combinatorics. Quite complicated, but it works. And b is also some number that's between here and here, and again, there's a combinatorial description. Moreover, if you try to integrate something, then he finds that there is actually some kind of vector distribution, and in fact, your measure is concentrated on the complement to your G or in that representation. So there is some G binary submanifold in there, so that your measure is actually concentrated there. So I will explain this in geometrical terms just in a second, but this is what you get. And how does he proceed? Well, it's groups here, Lie groups. It's K and K decomposition, combinatorics, cones, so on. All right. So what are the difficulties in this theory? So we want to have something that covers simultaneously, cubic surfaces, linear algebraic groups, and so on. And the asymptotics of such height balls, especially in the Delic setup, where you have all these factors in finite places and so on, that was an open problem in many cases. So the goal, therefore, is to develop some geometric framework that would be applicable both analytically, which means at the reals, at the p-adics, but also in the Delic setup, which would give us these Euler products. And that would be applicable to cubic surfaces and algebraic groups simultaneously. And that would be applicable to rational and integral points. We don't want to distinguish rational from integral points. So that's the goal. So now comes the talk. That was the introduction. So we start with some number field and some projective algebraic variety with the field, projective, for example. So look at rational points. And we'll be using the language of metrized line bundles, which is simply, choice of norms. If you've never seen a delicate metrized line bundle, you just think of, picking, square root sum of squares or something else that equals places. Now, doing that produces us a height. So it's very ample line bundle with an embedding into some projective space, and the projective space here is a height. It depends on the metrization, and that dependence will be carried along. So all definitions that we will make will incorporate the metrization, the choice of metrization. And what you know about heights is, so you have one projective embedding, you have another projective embedding, you can sort of compose them. Projective embeddings into a semi-group. You can re-embed this in projective space, and you shouldn't be surprised that the heights then multiply.
Did you say what Adele's, the finite Adele's were? Before?
I didn't say what Adele's.
I think you should.
I should say what Adele's are?
Yes.
Well, okay, so Adele's. Well, it's a restricted product, right? Over all places. P restricted times the reals. And restricted means that, well, it's just vectors, xp, and you want that for almost all places this sits in some complex that you have in there, which is cp. For almost all p. Okay? It's a range and so on. And then you can look at the other points on algebraic variety, for example. So essentially it's looking at all congruences simultaneously in practice. So now,
so what class of inner products on ample line bundles you're looking at? You take a pull back from projected embedding that is compatible with the.
Yeah. So another way, what is an adelic parameterized line bundle? So what does it mean? So we write L and the same as norms, right? So L is very ample. So I have some embedding into a. This is what L does. Projected space. Let's do it over Q, so simplest case over Q. Now, and as I said, the actual point will be an integral point, right? The representative there. Because the only choice that's really out there is I can pick a different norm at infinity, say. So I have a choice of norm plus norm, in this case at infinity, which means square root of some squares. Or, I could put some coefficients here. I could look at ellipses rather than balls. That's all allowed. But they should be compatible, right? There should be some distortion, but they should be compatible.
So, I mean, how does the rationality of X determine which inner products you can use? That was sort of the question I was asking.
The rationality, I mean, I'm not using anything about X. X is just equations in PN, some homogeneous equations.
Right.
So I'm looking at points.
But in this case, they would be
solutions of these equations. So I'm looking at rational points in Pn. So I have also x0, xn in Vn plus 1, primitive, minus 0, up to plus minus, which satisfy equations that define x. Now, of course, I would want to pick equations which have integral coefficients. This projective representation, I can do that. So that's called choosing an integral model for my variety, just clearing the denominators. And then, for those fixed equations, I mean, of course, it could be different integral models, but let's fix one. And then, that's what we have. We're just looking at solutions to these equations. And we are organizing them by height, maximum coordinates, for example.
But so the brief answer to the question is that as long as the image of X has equations defined over Q, then you look at the induced. Then you look at the induced metric on.
I look at variety defined over Q, so X over Q. So I have equations in this coefficient in Q, this coefficient in Q, right? Then I pick an integral model, I clear denominators, and then I have to like this. This is where I do that. But if you want to think differential geometry, the trice line bundle, with a line bundle, just picking an S1 subbundle in there, so that you can say what is the length, what is the height, what is the norm of the section. That's all there is to it.
Yeah, so it's compatible with the Q structure that I was asking about.
Yes, so, and the compatibility with the Q structure, adelically means that at almost all places, your norm comes from an integral structure that you pick. Okay. That's adelicate. And in many proofs, since you're changing the integral structure from time to time, you don't want to carry along these changes. So therefore, you admit a priori that at finitely many places, your sink is up to rescaling. But at almost all places, the periodic norm that you pick actually comes from the integral structure, and that's well defined. So that's how it's done precisely. So that's a high formalism. And for example, if you have a metrized canonical or anti-canonical line bundle, it will give you a measure. And so I will down how to do this measure. You pick a point, you pick some local coordinates, And then locally, you just write the length of this times this. This is just your Haar measure on the VIX on FV to the dimension of the variety. And it's normalized in some fashion. And then it's a local measure, sort of locally around the point. But when you change coordinates on your manifold, you're introducing, absolute values of the Jacobian, and things are set up in such a way that it disappears. So this thing extends to a measure on the whole of XFV. Then you would want to integrate something like this. And what do you get?
It works because an integer matrix has determinant 1, or an invertible integer matrix has determinant 1.
Something like that. That's why it works. So it works because it works, and when you integrate, you get number of Q points over Q to the dimension. And that's what we saw before, P plus 1 over P for the P1 and P squared plus 7P plus 1. So that's a formula that now can be applied. Suppose you want to do it over all times simultaneously. Then you would want to multiply these things. And when you try to multiply these things, you begin to realize
conjugates of variables. I'm a little bit confused about the notation. You're looking at a top form, so it should be that times the dx1 dxb times conjugates.
There is no conjugates. So there's VI, right?
So when you
let's say reals, VIX. So this is just a form. Well, yes, over the complex numbers. Let's see, over the complex numbers. Well, you have a top degree differential form, so that's what you have.
Right. So if you wanted something you could integrate on a complex manifold, you take a section of non-aligned times its conjugate.
Yes, that's what you do. So, and that gives you a measure, right? And then you integrate. Now, of course, with the reals of the complex numbers, you won't see anything like this. You'll see something. Well, what you'll see will be exactly the residual volume that I explained in there. So you see exactly the epsilon thickening and then the limit. But at the p-adix, you see you get a formula that for almost all places looks like this. And when you start expanding this, like the Weyl conjectures will tell you that the number of p points on a projective variety, it starts with p to the dimension, or maybe number of components, but we don't have it here. And then comes the next piece. And the next piece is going to interact, when you get 1 over q. And in the other product, that's going to be troublesome. So you need to regularize that. You need to cancel it out. And so how do you do it? You need to do it uniformly for all places. And this is what you do. You look at the L function. It's sort of the envelope of 1 minus 1 over p. But now you have to look at the Artin L function for the Galois representation of the Picard group of your variety. And that L factor put in here, this measure will be convergent. But of course, now you messed it up. You sort of have to compensate for that. And how do you compensate for that? You take the residue of the corresponding Artin L function at 1. It has a pole. It has a pole of some order. But you take sort of its residue, and that number you put in front. And of course, at finitely many places, you can change any way you like. But then the change has to be compensated in L function. So you can increase or decrease the number of places you take. But so either you allow this or not. But so this is sort of a standard adelic regularization. So, and once you understand this, you can define some Tomagawa number, which is simply an integral over, let's say, the adelic points of your field, or over the closure of rational points in the adelic points in the direct product topology, if you like. So, and that's a Tomagawa number, and that's a tau that appeared in Mining's conjecture before. It was alpha, beta, tau. That's a tau that appears in complete generality.
Tau for Tomagawa.
Tau for Tomagawa, yeah. So, now, so that's the number. And now I want to do this in the quasi-projective situation where I have variety X, projective variety, at the complement to a divisor. Right? This is a sub-variety. And I'm looking at a similar construction. I start with the metrization of, let's say, the canonical line bundle, and this is what we just discussed. There is some kind of Tomagawa measure locally. But if I have a metrization of a log canonical line bundle, then I get a measure on the open part, on U of F is local field here, like the reals, for example. And you've seen this measure in the groups already set up. It's a Haar measure. So here I'm explaining that it's essentially the Haar measure of the group. But if you don't have a group, then...
Wait, which example were you doing? The canonical bundle and the...
So if I have, we just done on the previous slide, what happens when you have a trace canonical line bundle? Then you get the measure on X of FV. And if you have a trace log canonical line bundle, different line bundle matrice, then you get the measure actually on U of FV, U on the open part. And then, what is this measure? I mean, it's actually the Haar measure in the group context. I'm just interpolating between the Haar measure on a group and the Tamagawa measure that I just defined. And we can look at varieties that are neither groups nor projective, and then explaining how to get measures in this context. So you get measures similarly.
So it's independent of the equigrammatic classification.
There is no equivariance here to begin with. Here, you're not using anything.
I mean, in general, it's, but here you're saying in this example, when you take an equigrammatic classification and then take the complement of
The boundary, then you get this.
So, excuse me,
Yeah.
does this have to do something with the Chambert-Loir measure?
Well, that's joint work with Chambert-Loir.
Okay,
So I don't know whether
okay. So
that's in our joint paper. So you can call it Chambert-Loir measure.
I don't know the language, just I don't know.
So
Okay.
now, once we have that, we have some other effective divider. Let's say with support of this D. And let's suppose that is equipped with a metrization, so you know what the norm, the length of a section is. Then you can define a height pole with respect to that, the trace line bundle. And then you can try to compute the volume asymptotics. So you have the height, and then you have a measure. Now you can integrate. And so what's the volume? Now to compute this volume, we use the Mellin transform. And this is where Igusa integrals come in. And the Mellin transform, well, I'm just rewriting it here. And if you know the analytic behavior of this data function, Igusa data function essentially, you know what the poles are and residues of those poles, then you can conclude what the asymptotic is. So now there are some assumptions. We may assume that our boundary is stratified by irreducible components. Let's say they're smooth, intersect transversally. We can always achieve this by blowing up. And then we look at these kind of strata. So this is intersectional dividers, and these are sort of the other strata. So let me have a picture here. So we have some kind of stratification and so strata. So these are all components. The alpha, and this is the alpha. This the beta, the alpha prime. And so we're going to look at strata. These are the strata that are there. So this is the alpha 0, the stratum. So now we can write the divisor D, and this is what our divisor is, D. That's the support of the divisor. There are some coefficients here, and we can write L also in terms of the boundary components with some other coefficients. And now we're going to compute this Mellin transform, and we're computing it in charts, introducing partition of unity, and essentially we're going to localize our computation to these strata, to the strata. And in each stratum, after a change of coordinates, what are we seeing? Our integral is going to be essentially a product of integrals of this form, dx, let's say 0 to 1, function of s. So with a little bit of geometry, you are reducing, this computation to a product of integrals of such form. And, well, then you can read off the analytic properties of these Igusa integrals in terms of the geometry, in terms of the stratification of the boundary. So what's the answer? You get a resistive convergence, which is, I'm just looking at all these linear functions in the exponents. The order of the pole is simply the number of those gadgets where you get equality. And the leading coefficient is the sum of the integrals where, you have the pole of highest order. Now, let's do it over the delts. Over the delts, it's the same theory, except...
Wait, the leading coefficient is the bottom stratum, you said?
So the leading coefficient is like this. So You see, when you have a product of such integrals, essentially you're picking up 1 over product of its alphas, right? Times what? Well, times the residue, times some kind of volume here. And that volume is essentially some residual measure on the stratum corresponding to this dA of, let's say, FV, some kind of volume for some residual measure. That's the Magawa measure that we have. And so that's what's the leading coefficient.
So I just wonder, the bottom stratum corresponds to what part of the asymptotic expansion?
The main part, the smallest dimensionals. The more things come together, the higher you are in co-dimension when they come together, the bigger the order of the pole. Because
Right, but I mean, so that's the leading term, and the coefficient of the leading term will be computed on the stratum.
it's the volume of the stratum.
Okay.
Yes. And to connect it to the previous result of Macron, that's exactly the localization of the measure at the boundary. That's what I play out here. So the global theory requires some kind of adelic integral in this fashion. So we have some adelic things, and so we need an analog of the final condition. We need some cohomological vanishing that has to do with kind of regularization of the other product. Now we're introducing the analog of
You mean to show it's well defined?
to show that it works, because
You need to get it to work.
yeah, you need to get it to work, you need some kind of vanishing. In the final case, in the projective case, you have that vanishing. But in the quasi-projective case, well, so we have some Gallo module that's replacing the Picard, lattice Picard module that we had before. We call it EP, it's from Euler-Poincaré. So some virtual Gallo module, and then we introduce some convergence factors, which are L functions, arted L functions for this module. And then we introduce this, we get a global measure on the adels of U, and well, we have a measure. We start now with an adelic metrized line bundle, we have a height function, we have a height pole, adelic height pole, and we integrate. And what's the volume asymptotic? It's computed by an adelic Mellin transform, and that in turn is the product of local things. And to regularize it appropriately, to understand it appropriately, we really need to know what it looks like at almost all places. So this is what it looks like in general. By the local analysis that we just did, these things converge here. They pick up a pole somewhere where this is exactly equality. But what makes the whole theory possible is that these Igusa integrals at almost all places have this uniform geometric shape. And that's kind of a miracle. So without doing any detailed computations, you know that this is what you will get. Let's analyze this formula. So what happens when S alpha times lambda alpha minus 2 alpha equals 1? This is where you're going to pick up some pole, right? Well, here we see q minus 1, here we see q minus 1, this cancels. So what's left? Sum of the whole strata, number of the 2 points of the strata over q to the dimension. Well, that's the number of points on x over f cubed. They're summing over all strata. So that's the number of points on the variety of the finite field. So let's analyze the poles. Where do we have poles? As we said before, the number of f q points is q to the dimension. So the pole comes up when the dimension of the stratum is 1 less than the dimension of the whole thing. Well, when is it the case? When we're looking at the alpha, the divisor. As soon as two divisors intersect, you're higher per dimension. So in other words, the strata can be very complex geometrically. They are, essentially arbitrary varieties. But the only thing that we need to know for the regularization is how many boundary strata do we have? And that's it. And we are able to say what the pole is of this other product. And the answer is...
How many top-dimensional strata?
Well, there are only dividers, the top-dimensional dividers that we're looking at. And so it's the number of these alphas that plays a role. And so then we look at A is the maximum, it's those linear functions that are correlated. This is the number of alpha wave equality, B is the number of the gadgets. And then let E be the divisor A minus B, it's supported in the boundary. And so then the leading coefficient, the residue, so to speak, of this data function is, this kind of integral, essentially localized over there, and then we have a Siberian theorem that translates analytic properties of the data function into asymptotic properties for the hyperpole, so boom, as a closed form. Now, so this is the theory, and now we want to apply it. For example, we want to count number of integral points on some variety, quasi-projective variety. Now, integral means, confined to many places, there's S-integrality, there are sort of interesting things. So this integrality. And a sample problem that's already quite interesting is equivariant compactifications of a unipotent group, for example, the additive group. So from complexity point of view, so what are equivariant compactifications of GA squared? Well, essentially we need to classify pairs of commuting matrices, because it's just two things that commute. So it's representations of GA squared, commuting matrices. So it's a bad classification problem. And you don't want to do it. So the answer will be not in terms of representation theory, it will be in terms of the geometry that we're going to see. In other words, in terms of the boundary of equivariant compactification of our group. So here is the theorem where we interpolate between the group and the projective thing, where we allow integrality with respect to different boundary strata. So for any subset of the boundary, we can now declare U to be the complement to X of this subset of the boundary. So it's a little bit bigger than the group, and it's smaller than X in general. So, and if this is empty, then we're looking at rational points. Okay, so then we have some line bundle, metrized line bundle in X. Then we count points, so bounded height, integral points. And how do we do it? Well, we extend the height pairing from one metrized line bundle to the whole Picard group, to all metrized line bundles, and from rational points to ZLs. So we write down a generating function, some height zeta functions, height to the -1, and sum over all integral points. We apply some harmonic analysis on the Delic space. It's, in this case, in the commutative case, it's a Fourier expansion. In the non-commutative case, it's more interesting. Eisenstein series come in and automorphic forms and so on. But so here I'm doing the simplest case. You have a sum over all characters of Fourier transforms. So what is the main term? The main term, the trivial representation, gives us an integral like this. Well, this integral is exactly the volume integral that we just computed. So, and we know what the asymptotic is. For the minus log anticanonical, we obtain B log BB minus 1, where B, this time around, is the contribution, the rank of the Picard of the open part, and then for each place in S, this is where S integrality comes in, we are picking up a term, contributes to the pole, and what is it? It's a dimension of the Clemens polytope of the stratification. So I should tell you what the Clemens polytope is of the stratification. Each divisor is a point. Dividers intersect, there is an edge. Three dividers intersect, there is a face. So that's the Clemens polytope. It showed up in the variation of Hough structures in the works of Clemens and Griffiths from a long time ago. And it plays a role in our analysis. In fact, the things contribute to the main pole in the asymptotic. And so what's the numbers that show up here? Well, alpha is some rational number, beta is some Galois homology, essentially. It's a Grau group. And tau is this Tamagawa number, which is Tamagawa number of the dells for places outside S, and then residual measures at these strata, Clemens polytopes that play a role in this Tamagawa volumes for the measures that are defined these strata. And we also need to look at the non-trivial characters after all, and to show that the sum over all those non-trivial characters doesn't contribute. So what are we looking at? Now, when there is no boundary, when we look at rational points, those contributions are smaller. And the reason they're smaller is because in harmonic analysis, you have this principle of stationary phase, right? So you have something, and now you have a character, and the character is sort of e to the I, and then like an AX, right? So you're going to see some oscillations, well, and the thing is going to concentrate along AX equals 0. But ax equals 0 is some kind of subvariety in your variety. So that's the 0 set of your rational function here. So therefore, you're not going to be surprised that the corresponding Euler product, since it's a subvariety in higher codimension, it's not going to contribute to the main pole. So this is what happened in the rational quantity. But in the integral context, these do contribute sometimes. And, well, so here I've analyzed, so to speak, one Fourier coefficient, but when you do Fourier series, you need to make sure the Fourier series converges. So you have to sum over all terms, and you need uniform estimates, and that's integration by parts, and all those things in Fourier analysis that you need to do anyway. But what's interesting for the analysis in the integral context is that both actually do contribute. And there are some geometric oscillatory integrals which in general have this shape. This is the height in local equations, and then there is this character, which is e to pi I, and then there is something, and there is x1 to the s1 x2 to the something. And this is just just compact support, smooth function compact support that comes from the partition of unity. So we need to analyze these things, and we need to get poles exactly, pull out the poles exactly where the oscillations occur, and get some uniform bounds and normal recontinuation of this kind of integrals and complete generality of the geometric setup.
In the last 10 minutes, I've been imagining you as a physicist making a quantum field theory computation. But I have no idea what.
Well, it's the algebraic analog of that. I mean, yes, we are computing oscillatory integrals and trying to pull out, the leading terms of the pole where exactly where you have. So, and then you need to sum over all of these. So we need uniform estimates, uniform bounds for these kind of oscillatory gadgets. And we are doing it in the reals and in the PIX, of course, and it works. And so after our work, there were some similar results by Pluckers in this sort of the analytic one, the corporate one. Now, to summarize what we have done today is, so we looked at these geometric Igusa integrals, which are Mellin transforms. They allow us to compute asymptotics of essentially all balls which arise analytic and analytic geometry. So you give me any set of polynomial equations and polynomial inequalities, and I'll tell you how to compute that. Now, it's going to be in geometric terms. So if you have a concrete equation, it may be difficult to actually compute it. But sort of the beauty of the subject here is that you never want to actually compute the volume. So when you have a conjecture and you prove some result, you're actually comparing the metrics here and there. You're comparing the integrals and not the result of the computation. And so that's sort of the way things proceed. And so we can compute asymptotics of height poles. We use the spectral method, L2 theory and expansions to establish asymptotics for rational or integral points in bounded height. The analysis of the spectral side leads to interesting oscillatory integrals, and in the context of additive groups and the toric context and semi-simple groups, we've proved all the asymptotics, but there are still some other cases where more work will be done, like unipotent groups, for example. We haven't addressed yet generally unipotent groups. And finally, the framework I presented interpolates between Magnus conjecture, originally for rational points, and these results about integral points, going back to the work of Rudnick, Sarnitz, and other people. And it's a perfect match. So that's it. Thank you. Thank you so much.
Are there any questions?
Do you have examples of varieties when these formulas are exact, like in some cases? Your counting is given by volume computation.
Yeah, so there are examples, there are counterexamples to Magnus conjecture. So that's we found. But they come from geometry, and they are actually easy to explain. The equations go like this. So let's look at something like this. X0, Y0 squared, cubed, squared doesn't matter. X1 squared. So this is a hypersurface in P3 times P3, and it's a by degree 1, 2 hypersurface. So we're looking at rational points satisfying this. So what is the height? What is the anticanonical height? So this is our x. So the height of x and y is simply maximum, let's say, of the axis. Now, so we have, in PC, it's 4 variables, minus degree 1, so we'll take this to be cubed, times the maximum of the y's, and here we would take 4 minus 2, you take squared. So that's a height. And so this you want to be less equal than b. So, and if you had taken, for example, 3 instead of 2, then the height would be, again, maximum of the x's times maximum of the y's. Let's say this time 4 minus 3, it would be to the 1. Right? So let's think about this geometrically. So if you project onto the y's, then you're seeing a linear equation in the axis. A linear equation in the axis, it's simply over the P3 of the y's, it's a P2 bundle. So it's an affine space. It's a 5-dimensional affine space. It's completely straightforward geometrically, right? So if you however project onto the axis, we're seeing a family of either quadrics or cubics, depending on what the degree is. So let's think about the cubic case. So the degree, let's say cubic. When the axes are all cubes, then the cubic surface is split. Let's assume we have the circle of one and a field as well. And at the very beginning, I said, well, if you have a split cubic surface, the asymptotic that we expect is going to be b log b to the 6th. So expect on split fiber b log b to the 6th. However, on the total space, right picard is 2. And on this hypersurface, it's just right picard is 2. So 2 minus 1 would get b log b. So b log b. So the conjecture predicts on a split fiber log b to the 6th, on the total thing b log b. So there's a problem. And finally, the fibers corresponding to cubes, they are dense. You can't throw them out. They're not that accumulating. They're really dense. So you have these split fibers here that are all over the place. All over the place. So, and even in degree 2, we are in trouble, because in degree 2, the fiber, when it's split, is a P1 times P1, and that also has B log B. And the total space is B log B. So, and the fibers contributing B log B are dense. So, there is this tension. So here we really have a counterexample, and in the other case you have a counterexample at least to the leading constant. It can't be a Tamagawa number, because you throw out a fiber, and the delicate integral doesn't change if you throw out, how to mention this, you throw out subparacters, the delicate integral is the same. But the analysis, the arithmetic tells you it can't be right. And you can also mess up this exponent by looking at some singular varieties. If you start messing with singularities, you can actually get an exponent from B. That's not what the prediction was. You get from volumes.
Are there any other quick questions? Well, if not, then let's